When testing navigation systems, it is easy to question whether there is a need to simulate at all. As systems increase in complexity and capability, the need becomes more and more important. Live testing of inertial navigation systems can be extremely costly and time-intensive. The need to exercise accelerometers and gyros while flying mission-like trajectories can make live testing prohibitive or highly infrequent. Use of SimInertial allows users to create a high-quality simulation environment to simulate navigation algorithms for hardware-in-the-loop testing. Spirent system will generate delta thetas and delta Vs specific to the identified test interface coherently with GNSS RF signals. The flexibility afforded by SimInertial permits repeatable testing with an array of EGI or IMU systems. Looking at what makes up the SimInertial capability, we have a dedicated rack mount controller PC with timer cards for synchronization, RS422 cards for delta data transmission. Honeywell devices may require the ISRS card. SimInertial will receive all truth motion and configuration data from SimGen via Ethernet streamed data. It will apply gravitational and defined error effects. Support for multiple devices is possible. On the SimGen side, all capability is authorized via license file. Scenario creation when utilizing SimInertial will occur via SimGen. When running, SimGen provides trajectory data to both the RF signal generator via PCIe and to SimInertial via streamed aiding data messages. In SimGen, users will define the desired INS model, any applied errors, the IP address of the SimInertial machine, and the message type for barometric altitude aiding if used. Signal generator chassis will create the simulated GNSS RF signal undergoing the SimGen defined trajectory and will provide timing and synchronization signals to SimInertial to ensure data and signal coherence. Support exists for a variety of IMU and IGI interfaces. The architecture does support generating additional interfaces as necessary. Inertial measurement units, or IMUs, are systems that consist of at least 3 accelerometers and 3 gyros. These devices measure angular rates and accelerations, where gyros integrate angular changes, or delta thetas, to provide attitude, and accelerometers integrate velocity changes, or delta V, to provide velocity and position measurements. They're strapped-down systems where the IMU mount is rigid and orthogonal to an airframe. They provide good short-term accuracy, but are subject to long-term drift due to instrument biases or cross-coupling. They are extremely resistant to external interference. Testing of systems that contain an IMU, both IMU and GPS signals are simulated. Simulated delta V and delta theta measurements are generated according to the vehicle motion in the scenario. These will be coherent with the simulated GPS signals. Due to the fact that most IMUs lack a test interface, simulated delta V and delta theta measurements are generated to emulate the output of the IMU. In practice, the IMU itself is completely bypassed and signals are directly fed into a navigation system, which will in turn create a blended navigation solution. There's a notional interconnect diagram when conducting IMU system level testing. The SimInertial PC will provide simulated delta thetas and delta Vs to the system under test. The GSS 9000 signal generator chassis will provide RF signals to the GPS receiver, which can be combined and blended in the system under test. Synchronization signals between the GSS 9000 and the SimInertial PC will keep data and signal coherent. And optionally, control, power, and data logging can be handled by an external PC. Integrated GPSInertial systems, or IGIs, collapse our previous example into a single unit containing the IMU and GNSS receiver. These robust systems are capable of providing 3 navigation solutions: GNSS only, pure inertial, or a blended GNSS-INS, usually in the form of a Kalman filter. IGIs benefit from GNSS's lack of long-term drift, the low short-term errors of the IMU, and the ability to maintain system integrity by producing multiple navigation solutions. The inertial side can aid signal track during high dynamics or when subjected to interference, and the GPS GNSS enables calibration of inertial errors. As was the case with our IMU testing example, for IGI testing, GPS and IMU signals are simulated. Simulated delta V and delta theta measurements are generated according to the vehicle motion, coherent with the simulated GNSS signals. Simulated delta V and delta theta are input to the IGI through a special test interface, bypassing the actual sensors. The simulator can generate perfect delta theta and delta V, or use inertial error models to simulate the measurement errors produced by actual IMUs. Similarly, our notional IGI testing interconnect is shown here. The SimInertial PC will generate simulated delta V's and delta thetas. The GSS 9000 signal generator chassis will generate GNSS RF signals for direct input into the IGI. External PCs can be used for IGI control and data logging. Power and I/O and data capture can be handled with the IGI test station. SimGen, in combination with SimInertial, is capable of simultaneous simulation of up to 4 independent inertial units. Each unit can be specified with a unique aiding offset for simulation of realistic dynamic effects. These offsets are defined relative to the vehicle center of motion. As seen in the diagram, each inertial unit will require a dedicated SimInertial controller PC, each receiving specific configuration and sensor model data for the defined system. While SimInertial allows for idealized testing, error effects can be defined during scenario creation to allow for realistic performance testing. The error model is generic and defined in the STANAG 4572 document. This model allows for deterministic error injection in the form of misalignment, biases, and added scale factors. Additionally, the capability for stochastic error generation exists via random walk or white noise in the sensor data, Gauss-Markov errors to model random offset in the sensor output, or dithering effects via a blue noise model. The magnitude of the defined errors is dependent on the quality of the individual sensors and program test requirements. Inputs to the error model can be found in manufacturer specifications or datasheets. Additional error models can be incorporated by utilizing the existing error model interface and a customer-defined DLL. Due to the volume and rate of data being generated, log data is written in binary format. After completing a scenario run, if data logging has been enabled, SimInertial provides a utility to convert the truth data to ASCII text. 4 files will be produced: truth data as received from SimGen, truth data interpolated to the INS sensor rate, and 2 files for the delta data outputs for each set of sensors. The integrator, when used in conjunction with the SimInertial log files, can integrate back the delta data and calculate the error between the truth position and the calculated INS position. The integrator generates an INS solution based on the vehicle dynamics, sensor scaling, and inertial sensor errors. As previously mentioned, simulation of barometric aiding data is accomplished via Simbaro. Aiding messages are sent to the UUT on the 1553 bus via a 1553 interface card in the SimInertial PC. Simbaro is capable of functioning as both a remote terminal, wherein another bus controller executes the data transfers, or as a bus controller, where Simbaro executes the data transfer to the UUT. Simbaro provides the capability for error injection to the aiding message. This can be applied as a fixed altitude offset, ramping errors with configurable start times and rates, periodic errors on a sinusoidal model, or on a Gauss-Markov noise model. Options are configurable via the SimGen interface in the INS model GUI. When performing hardware-in-the-loop testing, the fidelity and accuracy of the supplied 6 degree of freedom trajectory is of utmost importance. The quality will affect the resultant GPS, and the inertial delta data reflects the desired dynamics. Inconsistencies in linear and angular data, such that position and velocity do not cleanly differentiate to higher order terms, can create issues in trajectory propagation and divergence of GNSS and inertial data. The magnitude of these errors in timing and truth data will depend on the trajectory, linear, and angular dynamics. When simulating, proper initialization of the system is essential for correct alignment. The input position information must be consistent with the simulated position to avoid alignment to an incorrect position or use of the wrong gravity vector. Several meters of error can have a direct impact and significantly degrade the performance. Additionally, the sensor update rate must be consistent with the UUT being simulated. This is device-specific and must be verified by the manufacturer's ICD. Use of an incorrect rate will have detrimental effects on performance. Some additional useful bits of advice when looking into simulation. A basic scenario for inertial testing can be a good method to get familiar with the receiver and its operation. This can include very simple trajectories or exercising single-axis motion using the axial roll commands within SimGen. Validating all information about the UUT is extremely important to root out any basic issues of data processing, including whether a test interface is included on the specific model. Building custom tools for analysis of navigation solutions, the GPS, INS, and blended solutions can be very advantageous. Use of the SimInertial integrator utility is also helpful in post-scenario analysis.